So if you'll recall on Friday, we kind of left with discussing impulse. And just to ensure you have that stuff in front of you, we kind of had this as part of our discussion, and that is part of our discussion. Look familiar? Hope? All right. Now I'm going to ask a question. It's not obvious, but I want to see at what level you guys are able to think on a Tuesday morning. So I'm going to give you the situation, and I want you to see if you can tell me what the answer is. I have just a nice little bouncy ball. Let's say its mass is 50 grams, and I just drop it, and I am dropping it from like 2 meters from the ground. It bounces off the ground and returns to a height of 1.5 meters. And I catch it. So you've got, I think, everything you need to do this question. But I don't know. I don't know if you'll be able to or not. I'd like you to tell me what the impulse experienced by the ball was while it was in contact with the ground. You're going to have to probably think of some things to do here to figure this out. But maybe work together as a group, come up with a plan, and I'll see what your plan is, okay? Some method to figure out how fast the ball's going when it reaches the ground. So this would be the initial velocity just before it hits the ground. And then it bounces off the ground due to a force from the ground. So there's going to be some final velocity after it recoils. You have a lot of ways to do this. A motion equation would work, and that's fine. But it also has gravitational potential energy here and kinetic energy here. You could set those two things equal to each other. There's a variety of ways to go. You could also just have memorized that the velocity of something that is dropped will be square root of 2gh when it reaches the ground. I mean, you have options. I would encourage you to try and remember some of your options. But I probably would have started with mgh here, 1/2 mv squared here. Energy is conserved. It's a change in height. You're going to be faced with problems like this on the exam that are going to mix stuff together. And you have multiple options on how you can usually solve some of these problems. However, you needed to figure out the velocity. That was the probably the most important thing to do here, and recognize that this is what you're going to be shooting for. That's going to be momentum final minus momentum initial, which is going to be mv minus mv naught. This is the kind of stuff I'm expecting that you will put together. And this is certainly fairly straightforward once you see that. I think this becomes square root of 40. And this one is square root of 30. Did you guys get those? All right. What'd you do next? Yeah?
I put it into one of the P's was MV, and then I made down positive, or we made down positive. So negative 5.4 plus 6.3, which is square root of this, and then times the mass of 0.05.
All right. I was hoping that you would have said something about the direction, which you did. Excellent. So our final velocity is negative 5.4 minus our initial velocity of 6.3. Is that what we got? Any question about this? So got negative 0.59. Is that what you guys got? That's what I got. Is that what you got? Is that a yes or a no? I mean, make sure my arithmetic is right, but it's not a very big impulse. Yeah.
Wait, why did we subtract 6.3?
It's final minus initial. Right? This minus sign.
Oh, okay.
Right, it's the difference. Okay. And you made down positive,
Yeah.
so I had to make the upwards velocity negative. These are all the little details you guys tend to get wrong. So you understand that if this were a multiple choice question, assuming you would figure out to do something like this to figure out the velocity, the answer that's going to appear there is going to have at least one in which I ensure that I forget to make the direction different, right? You know that will be one of the choices. I'll always do that. But I want to go a little further here. This is kilograms, meters per second. What direction was the impulse on the ball? It was upwards, right. Came out to be negative, so the direction of the impulse was upwards. That means that the ground pushed upwards on the ball. Does that make sense? Sure. The ball was going down, and when it was done, it came back up. No big deal. All right, let's try another one, because I think we need some practice. So, I have a block of wood sitting on a table, and I'm going to fire a bullet towards the block of wood. The bullet travels at 300 meters per second and has a mass of 0.005 kilograms. When the bullet emerges on the other side of the wood, it has 75% of its kinetic energy gone. What impulse was experienced by the bullet? Understand the question? Okay, give it a shot. See if you can work this one out. I don't think this one's as hard. Did you find the original kinetic energy?
Yes.
All right, so 1/2 times 0.005 times 300 squared was 225 joules. Is that what you did first? So after it passes through the piece of wood, it has lost 75% of its energy, so it retains 25% of its energy. So the amount of kinetic energy afterwards is like, what, 56 point something? All right. Now you need to work this backwards and figure out what the velocity is after it emerges. You can't use the energy. So you have to set that equal to 1/2 mv squared to figure out the velocity after it emerges from the piece of wood. And when you do that, you get 150 meters per second. Now, it was always traveling in the same direction. It was always, always in a positive direction. So, change in momentum. There's not a whole lot here, but this is the kind of stuff I'm going to expect you guys to do. I mean, this is the only thing that we had last Friday. Everything else is stuff from first semester. I don't know what this works out to, but it's like 7.5 or something, or 0.75. Does it make sense that it's negative? What direction is the impulse? Left. So that means that it experienced a force this way while it was in the block of wood. All right. I want to start here with our discussion today, but I have some fear, all right, because we're having some challenges. So maybe perhaps we need to do one more just to make sure, because I'm thinking we got some troubles. So back to this example, please. So if you would pull this example back up, I want to have a reminder that the impulse was negative 0.75, because I'm going to erase everything that's here. All right, get all that out of the way, out of the way. So this is new notes we're going to add to what we talked about on Friday. This is no longer an example. I'm just using this example as our discussion. And I want to get rid of the stuff about energy here and just talk about what we saw. The bullet passed through the block of wood and left at a velocity that was half of where it started. Now I'm going to ask some straightforward questions, and I hope that you can answer these. We know what the impulse was. That has to be related to the force, because impulse has two parts. The block pushed on the bullet, and it pushed to the left. That's why the arrow is drawn, to the left. That was the direction of the impulse on the bullet. Now I'm going to ask a very straightforward question, worth writing down. Is the bullet in contact with the block for a different time than the block is in contact with the bullet? Say it again, but is the bullet in contact with the block for a different time than the block is in contact with the bullet? I guess what I'm trying to say is, can the block be touching the bullet if the bullet isn't touching the block? No, it can't, right? So, and I'm not trying to be confusing. I just want you to think about this for just a moment. The block applied a force to the bullet. At the same time, the bullet had to apply a force to the block, right? Newton's third law. In fact, Newton's third law would say that the force experienced by the block had to be equal and opposite to the force experienced by the bullet. Doesn't that have to be true? I mean, that is the Newton's third law. So if the block was pushing on the bullet was pushing on the block. I don't know how many different ways I can say that, but I'm just trying to state Newton's third law. Now, the time was the same for both. Right? T had to be the same, which suggests, and I hope you're seeing where I'm going with this, that the impulse experienced by the block had to be the opposite of the impulse experienced by the bullet. By the way, there is a symbol used for impulse. I never use it, but there is a symbol used for impulse, and it could be used on your exam. So since we're having this conversation, and I'm sure you'll love this, the symbol for impulse is a capital J. Because that makes sense, right? But look, I'm just telling you like it is. Those aren't units, that's just the letter used for impulse. I don't ever use it. I don't know why they wouldn't use a capital I for impulse. Except we use capital I for, you're going to love this, moment of inertia. Something you're going to learn later. So yeah, the letters, it's silly. So I'll stick with what I have here. But I'm about to show you something or prove something to you. So can we all buy into the fact if Newton's third law is true, then for every impulse, there's an equal and opposite impulse. That's really what this is saying. Because the time has to be the same, one thing can't touch another without still being touched by the first. So because that has to be true, and because for every force there's an equal and opposite reactive force, for every impulse, there's an equal and opposite reactive impulse. This is Newton's third law, just applied to impulse. So this will always be true anytime one object touches another. Everybody understand so far? All right, well, you need to follow some algebra. This is going to hurt. That would also have to be true. We're going to derive something here that has important value. So pay attention. I'm not going to use block and bullet. Can I just use object 1 and object 2? That will make it a little bit easier, so we don't, because we're going to have some other stuff. So I'm going to say this is object 1 and object 2, because it would be true for anything. Bless you. So this would be P1 minus P1 initial has to be equal to minus P2 minus P2 initial. All right, final minus initial. I'm going to distribute the negative sign. So P1 minus P1 initial equals P2 initial minus P2. When I distribute the negative sign, it just flips those two there. We all good? Everybody see this okay? All right, I'm going to get the initials on one side and the finals on one side. Now, this is one of these statements that's really profound, and this will probably be the most important thing we learn all semester. But this says that whatever the momentum of your system was before two things touched, it'll have to be equal to the momentum of the system after the two things touched. This is a conservation rule, and it says that momentum is conserved whenever two objects touch. Conservation of momentum is a very powerful rule. It's derived from Newton's third law. And although we won't have a whole lot of time to apply it, not today, we're going to spend the rest of the week applying it, I want you to understand that conservation of momentum, believe it or not, is more powerful in many ways than conservation of energy. Because unlike energy, where there's all these different kinds of energy, and you're trying to track where it goes, there's only one kind of momentum that you've learned about, and this is it. So whatever the momentum of the system is before a collision occurs, has to be the momentum of the system after a collision occurs. That will always be true. Always. The problem is defining a collision. So we're going to be talking about a lot of different types of collisions, but defining a collision is the hard part in this class. So we define a collision as the instant before contact and the instant after contact. This is how we're going to define a collision. We define a collision as the instant before contact and the instant after contact. Because there's more things that have to be said about conservation of momentum to really put the whole piece of the definition together. For one, this was only true if the only forces that we're talking about are the forces between the objects. So we're talking about something where there's no external force. That has to be a statement. Now that limits us, because most things are experiencing an external force, like gravity or something. But in all collisions, we're only talking about the instantaneous moment before contact and the instantaneous moment after contact. In every single collision, momentum is going to be conserved. We'll see how that plays out tomorrow. We're going to do a bunch of demonstrations tomorrow. One more.
Good morning, and pardon this interruption. At this point, teachers,
right.
No student should be admitted to class.
I'm not sure I'm catching all of the nuance of what they're trying to do, but
at this point,
here we go. How about this time?
It's Tuesday.
No early release, I know. Sorry. Did it hurt your feelings?
Huh?
Did it hurt your feelings that there's no early release?
Honestly, yes.
Sorry. Yeah, you're stuck here. You're stuck here longer.
And that's such a cool thing.
Did it?
I think I'd rather
No.
hospital where they were
No.
knowing there's early release.
No,
than
Mr.
on
Schultz.
Tuesday.
What?
Don't do this to me.
Don't do what to you?
This. Mr. Schultz, I beg of you.
I'm not doing anything to you. I'm just trying to show you different problems. If I could just interrupt, if you could separate it out, you'd have the change in momentum in the x direction and the change in momentum in the y direction. You're going to have to do the trig to figure out what those velocities are. So it's just a little bit of trig. Did you successfully do your trig? And if you did, you got like 8.6 meters per second here, or 8.7 maybe meters per second there. It's just 10 times the cosine of 30. And then the next one would be 8 times the cosine of 30. So is it 6.9? Did you pick one direction to be positive and one direction to be negative? So if we make this way positive, that one's got to be negative. And in the y direction, I think the ball was traveling at 5 meters per second upwards. And then after the collision, it was traveling at 4 meters per second. So this is all I got to do. There's not a lot here. So all this struggle, sadness. Now let's do the part from Friday, which is just MV final minus MV initial. So 0.05 times negative 6.9 minus 8.7. And let's see, 0.05 times 4 minus 5. Know what you guys got? That's what I got. So this is negative 0.05 kilograms meters per second. I don't know what the other one is. 6.9 plus 8.7 times 0.05. Now, there's more to this. We're just doing some of the basic kind of math stuff. When I say there's more to it, I mean, we just ran some numbers here. And like I said, did a little plug and chug once we figured out what had to be done. But I want you to think about this for a moment, please, because this is where we need to kind of sharpen ourselves. There's an impulse in this direction. That was 0.78, and there was an impulse in this direction. That was 0.05 kilograms meters per second, kilograms meters per second. But that means the actual impulse, the total, was something like that, right? The wall pushed on the ball in that direction. You could use the Pythagorean theorem to figure out what the total impulse was. You understand? That's how you would have to do this. Because there's a little friction here, that's why there's an impulse in this direction. The ball stuck to the wall a little bit. But clearly the ball also got pushed this way a little bit. This is not what I wanted to talk about today, but we've done 3 examples. And it doesn't matter which one of the examples I pick, the next thing we're going to do is going to extend this. So I've given you 3 solid examples.